We're going to start this notes on probability with a little problem here. So, a bus arrives at the bus stop every 10 minutes and it's always on time, but you don't know what time it's going to arrive. How long will you have to wait at the bus stop when you arrive? So, you may be walking up to the bus stop and the bus may show up right away. Or you may walk up to the bus stop and it may take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 minutes for the bus to arrive. So, what we want to do here is we want to calculate some sort of um, arrangement where this might happen. Um, so, what we'll do is we'll say if it is a 10-second wait, that still counts as a minute. So, we're always going to round up. So, like 9 minutes and 40 seconds would count as 10 minutes. So, basically, our options are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And so um, we basically could try to do this a bunch of times, and we have no idea what time this bus is going to show up. Uh, so we could like simulate this in a certain way and do this a whole bunch of times. But basically, what we have here is we have a situation where we could have 10 different possible outcomes to this situation. Um, Now, you're probably only going to do this one time in real life. But when we're trying to find probability, what we try to do is we try to simulate what would happen if this happened a whole bunch of times. So maybe we write a computer program and then we have this exact situation occur thousands upon millions of times. And then we end up with what are called probabilities for each of these 10 outcomes that we have. So let's talk about probability. The probability of an event is its long run relative frequency. So basically, what it means to have a long run relative frequency, that means in the long term, how often something will happen compared to everything else. So essentially, what that means is we end up with fractions or percentages. So that's important. And remember, long run means in the long term. So basically, as we're going to infinity, like a very lot of trials. For any random phenomenon, each attempt, which we're going to define as a trial, generates an outcome. An outcome is what happened on the trial. So if we go back to our little bus example, each time we are waiting for the bus, that counts as a trial, and all the possible outcomes are anything that could have happened. So, since the question was how long we're going to wait, and we counted it only in minutes, and we always rounded up, our possibilities were 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Sometimes, instead of individual outcomes, we consider what we call events. An event is a combination of an outcome, a combination of outcomes. So, if we were rolling a die, we have six possible outcomes. It could land on 1, 2, 3, 4, 5, or 6. An event might be any of these types of combinations of outcomes. And there are lots of choices that we can have. So, rolling an even number, rolling an odd number, rolling a number greater than 3, rolling a number less than 5, rolling a number um, greater than 7. Now, if we roll a number greater than 7, obviously that's not going to happen on a six-sided die. But we could write that as an event, and then we figure out that the probability of that would be 0. If we want to know about combinations of outcomes, It helps if individual trials are independent. That doesn't mean that they always are going to be, but it does help. If trials are independent, then the outcome of one trial does not change the likelihood of another trial occurring. So, for example, when we were waiting for the bus, the trials were independent because if I was going to do this a whole bunch of times, I walk up, I don't know when the bus is coming. Knowing the outcome of the first time that I walk up to this bus stop is not going to change what would happen as I walk up the second time to the bus stop. That may have absolutely no relevance on it. And so that's why those trials are independent. However, if we're drawing cards on a deck of cards without replacement, trials are no longer independent. We call those dependent. So if it is not independent, then it is dependent. If we draw a club on our first trial, then we know that the next card is less likely to be a club, and it's more likely to be any of the other suits like a heart, spade, or diamond. This is why casinos use 6 decks for blackjack instead of one, because even though that doesn't make everything independent, it does make it a lot less likely for people that are trying to cheat the system and try and count cards to actually be able to keep track of things. If it were independent, it wouldn't matter what card came first. But because we're not replacing the cards, we can kind of figure it out. The law of large numbers says that the long run relative frequency of repeated independent events gets closer and closer to the true relative frequency, which we know is the probability, as the number of trials increases. So let's go to the internet and figure out why that is. I've already flipped a coin 3 times and it was tails each time. I'll toss it again and it landed tails again. So I have 4 tails right now. Right now, 100% of my flips have been tails. And if I toss it again, it could be heads or tails. It just so happened to be tails. What we have to understand about this is that just because I've got 5 tails in a row does not mean that the next one is more likely to be heads. It's not like the coin has a brain and it starts to say, oh, well, this is not close to the probability that it's supposed to be. And it also doesn't mean that tails is on a winning streak and that we need to ride the winning streak and that we think that tails is going to continue to win and win and win. It may or may not win. So I'll flip it again. Oh, heads won this time. But if we look at this, the probabilities are nowhere near what they actually will be. Now, what happens if I flip 100 times? If I flipped 100 times, what ended up happening was, in this case, I got exactly 50 of each. So if we notice our probabilities, these probabilities are now getting really close to 50-50. I'm going to flip it another 100 times. And it ended up that heads won a lot more than tails that time. Heads ended up winning, it looks like 55 times. And tails only won 45 times or something like that. I don't know. I didn't count very well. I'm sure somebody will correct me. But if we're looking at this, I tossed it another 100 times, and tails ended up winning more than heads. But if we look, these numbers are getting really close to 50-50. And I can continue to do this, and these numbers are getting really close to 50-50. Now I'll toss it 1,000 times just because. And if I toss it 1,000 times, my numbers are still really close to 50-50. Notice that tails actually won quite a few times that time, and our percentages actually got further away from 50-50, but not too much. So if I do another 1,000 tosses, I'm probably still going to be in the ballpark of 50-50. That's what the law of large numbers means. As I start tossing this more and more and more, my probabilities get closer and closer and closer to what they should be. Here's another example with a spinner. So I'll spin this one time. I landed on cyan, light blue. I landed on purple. Notice that my experimental probabilities are nowhere near what my actual percentages would be in the long run. But if I spin this 1,000 times, Oh goodness, I really hope it doesn't. Oh, there's a button where I can skip to the end. This would be really annoying. If I look at this, my experimental probabilities all end up being kind of close to what in theory they should be. It doesn't mean they are all the time perfect, but it gets pretty close. Now I'll do another 1,000 spins. I'll skip to the end. And if I look, all of these numbers end up being pretty close, at least within 1% of its theory. And I'll do another 1,000. And as we look, these numbers are once again pretty close. Many people misunderstand this law, and we already talked about this. It's not the law of averages, it's the law of large numbers, and it only occurs after you've had a large number of trials. This is why casinos have boards which post the last 15 or 20 outcomes. It tries to get people to buy into a lie. Don't buy into the lie. Basic probability rules. A probability is any number between 0 and 1. So, if on a problem, quiz, or test, you end up with a probability less than 0 or greater than 1, you are definitely wrong. Something has to happen. So, when there's a single trial, one of the outcomes must occur. And all of the possible outcomes are the sample space. So, if I am taking a look at some of the things we've talked about, the sample space of the bus problem was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The sample space of rolling a die is 1, 2, 3, 4, 5, 6. The sample space of flipping a coin is heads or tails. If we wanted to flip two coins and count them as some sort of combined thing, we could have heads, 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 tails, tails, heads, and tails, tails. So we could have four possible outcomes if we flipped a coin twice. And HT and TH are different because if I flipped those two coins, one of them could be heads, the other one could be tails, or vice versa. So if I'm looking at this particular situation, since heads and tails are equally likely, two heads is about 25% of the time, two tails is about 25% of the time, and one head and one tail is about 50% of the time. The probability of an event occurring is 1 minus the probability of it not occurring. So if we look at this example, if the probability of rain is 0.1 today, then the probability of non-rain is 0.9 today. And we can denote not A with A sub C, A prime, or tilde A. I will often use tilde A in my notes in class and the things that we talk about. Multiple events. Let's talk about disjoint events first. So if we have two disjoint or mutually exclusive events, that means that they share no outcomes. And all we have to do is add the probabilities in order to find the probability that one or the other occurs. A or B is this notation. So the little U symbol means union, that means or. Two disjoint events do not share any outcomes. Since you can only register as a member of one party, you can't be a Democrat and a Republican at the same time. We call these mutually exclusive. So the probability, if the probability of being a Republican is 0.4 and the probability of being a Democrat is 0.5, or I'm sorry, 0.45, all I would do is add together 0.4 and 0.45, and I get 0.85. That would be the probability of being a Republican or a Democrat. This also works for more than two disjoint events. So the probability of being a Republican or a Democrat or a Libertarian would be 0.4 plus 0.45 plus 0.05, which is 0.9. Now, obviously, that means in this hypothetical situation, we have another 10% of voters or people that are registered to vote that are affiliated with either some other party or independents that we would have to take into account if we were looking at the entire sample space. So the sample space would be Republicans, Democrats, Libertarians, and then we're going to have more things in there that we haven't been given information about. Maybe 3, 4, 5 more things. Or what we could do is we could just combine all of these blank spots into one category, which we will call maybe independence or something. But in any case, we would have to assign all of the rest of these people. There should be 10% of the population. You can't use the addition rule when you have events that are not disjoint. So if you look at this, that's clear. You cannot have 165% of people either being a senior or owning a TI calculator. So what's happening is there are some seniors that also own TI calculators. That means these are not disjoint events, so we need more information. Multiple events. For two independent events, the probability that both A and B occur is the product of the two probabilities. Recall from yesterday, I guess I forgot to change the notes, but recall from today that two events are independent if knowing the outcome of one does not change the probability of another. So this upside down U means intersection, which also means and. So for example, if we flip a coin and roll a die, those are independent events because the coin and the die don't talk to each other, and it's not going to be like, hey, I got heads, so you should be a 4. Those things are not related. So probability of heads is 1/2. Probability of rolling a 6 is 1/6. So the probability that both of those things occurs is 1/12. This also works for more than two independent events. So probability of rolling 3 6s is 1/216. By the way, this would also be the same probability as rolling 3 5s. That's kind of important to understand because just because the number that we're choosing is 6 is not the reason why it's 1/6. Each of these spots on a die have a probability occurring of 1/6. You can't use the multiplication rule when events are not independent, though, so you can't use this for dependent events. For example, if a class of 30 students has 16 females, then the probability of selecting two females is not 16/30ths times 16/30ths. It would actually be 16/30ths times 15/29ths, because you know that after the first female selected, there's one less person in the class to choose from. That's why that's 29. And there's one less female to choose from. That's why the top is 15. If we were choosing one boy and one girl, then there would be 16/30 and 16/29 as our choices. And we'd actually have to do a little bit more than just multiplying them together. We'd have to think about the order that they were chosen in if it was something that was kind of assumed or not. Summary. When you want the probability of A or B, you add the probabilities, assuming it's disjoint. And if you want the probability of A and B, you multiply the probabilities, assuming they're independent. Real quick, probability of rain in Aurora is 50%, and probability of rain in Naperville is 50%. What is the probability it rains in both places? Well, it's probably close to 50%. That is because Aurora and Naperville are right next to each other. And knowing that whether it's raining in Aurora or not is very much related to whether it's raining in Naperville or not. However, Aurora and New York City are not close to each other, and therefore, while there is some sort of weather relationship between Aurora and New York City, it's very, very minimal. And so these would be treated as independent. And so we can just say 1/2 times 1/2 equals 1/4.